In this video lecture, we are going to learn a very important concept in logic design, which is nothing but Karnaugh maps. Here, we'll consider all the basic concepts that are related to Karnaugh maps in detail. When we talk about Karnaugh maps, the very first question that comes to our mind is why they are being used for. Here we'll see it. And later, we'll go and explore how to construct different Karnaugh maps, whether it may be a 2-variable Karnaugh map or maybe a 3-variable Karnaugh map or maybe a 4-variable Karnaugh map. In that regard, we'll see how to construct such Karnaugh maps. We know how to represent a Boolean function with the help of a truth table. This is how we used to represent a Boolean function. This is just a random example. But later a person came and he developed a new method to represent a Boolean function, which was an improvement over truth table. And that person is Karnaugh, and the method he developed is maps. Since he was the developer and he preceded his name with the maps and called it as Karnaugh Maps, which is invariably called as K-Maps also. In case of truth tables, say for example 2 variables, we used to have 4 different rows which are 0, 0, 0, 1, 1, 0 and 1, 1. But in case of Karnaugh maps, we will have 4 different cells. Instead of rows, here we call them as cells. So if I ask, what do you mean by Karnaugh maps? To answer that in brief and in the best possible way, Karnaugh maps are the diagrammatic representations of Boolean functions. Now we'll see why Karnaugh maps are being used for. Let us start that discussion with the help of a Boolean expression. Just consider a random expression. When we apply Karnaugh maps to this, we are going to have reduced number of terms or fewer terms. So the next question is, what is the use of having number of terms reduced? If we have 5 terms, then we need 5 logic gates to implement that function. This tells that story. After using Karnaugh maps, as the number of terms are reduced, we require less number of logic gates to implement the same function. As the number of logic gates are reduced, the manufacturing cost is also going to reduce. That was the previous case and this is the present case. When we are in the business of constructing something, we should have a proper blueprint. The same thing applies for K-Maps also. We must have a proper blueprint. And the blueprint in K-Maps is known as the property of adjacency. First, we'll try to understand what you mean by adjacency property. We'll consider 2 cells with terms 0, 0 and 0, 1. These 2 cells are called adjacent cells because only one element is changing from cell to cell and other is remaining constant. We'll consider one more cell with term 1, 0. This is again adjacent to 0, 0 as only one element is changing. We'll take one more cell with term 1, 1. Now this is not adjacent to cell 0, 0 as both the elements are changing. Now we have understood what you mean by adjacency property. That is well and good. The next question is why there is so much importance given to this property. Why are we behind this property of adjacency? To answer that, we'll consider 2 adjacent cells with 0, 0 and 0, 1. The Boolean function can be written as a bar b bar plus a bar b. We can take a bar out and left with b bar plus b. We know that b plus b bar is 1. we'll get the Boolean function as a bar only. So the expression is reduced. That is why adjacency property is very important. Now we are ready with the blueprint and we can go and construct Karnaugh maps. Depending on the number of variables, we can have different K-maps, like 1 variable K-map, 2 variable K-map, 3 variable K-map, and so on. Here we will consider how to construct a 3 variable K-map. We'll have 8 different cells. Let me draw a map with 8 different cells. X vary this way and YZ vary that way. X takes value 0 and 1, YZ takes value 0, 0, 0, 1, and the natural tendency to write is 1, 0. But we cannot write 1, 0, as 1, 0 is not adjacent to a cell with 0, 1. So it has to be 1, 1. And the only left out thing is 1, 0. It takes its value here. Now we'll write all the cell values, something like this. And then we will test the adjacency property with cell 0, 0, 0. It is adjacent to a cell to its right, and it is adjacent to a cell below it, and it is adjacent to a cell with value 0, 1, 0, as only one element is changing. Now we'll consider one more random cell with value 1, 1, 1. We'll test the adjacency property. It is adjacent to a cell above it, and to a cell to its right, and to a cell to its left, as only one element is changing. This was with respect to the construction of a 3 variable Karnaugh map. Now we'll consider how to construct a 4 variable Karnaugh map. Here we'll have 16 different cells. Let me extract a Karnaugh map that I have drawn with 16 different cells. I let AB vary this way and CD vary that way, and AB will take value 0, 0, 0, 1. Again we may tend to write 1, 0, but it has to be 1, 1 and 1, 0. The same applies with CD also, and again it cannot be 1, 0, it has to be 1, 1 and next 1, 0. This was an introduction to Karnaugh maps, and in the next set of videos we'll consider how to group the elements and how to reduce the Boolean expression to fewer number of terms.